Hi. In this video, we're going to talk about stationarity. We're going to define the characteristic of stationarity and talk about different ways that a stochastic process can be stationary. Okay, so stationarity, sometimes we use the word homogeneity instead, but I'm going to focus on using stationarity. So it's a characteristic of a stochastic process, so x of t with curly brackets. And when we say the process is stationary, we mean that some property of the process is unchanging in time. All right, so it's referring to kind of changing properties, and we have to refer to a specific property, okay? Because there's lots of things about a stochastic process, lots of properties, and not all of them have to be unchanging in time. So let's talk about some examples. So we could talk about stationarity of the mean. So here, what we mean is that what we define here is that the mean of the process at time t is equal to the mean value of the process at time t plus r, where r is some shift in time. So if we shift forward or backward in time, the mean value is unchanged. Right? And that has to be true for all r. Okay, so it doesn't matter how far forward or backward. There can't be just some instance in time in the future where the means are the same by coincidence, but at other times it's not the same. That mean value has to be, oops, I'm sorry, I've got a subscript problem here. So this is the mean value of x still. So we're referring to the stochastic property x the whole way through, but at all points in time, the mean value stays the same, okay? And then when that happens, sometimes we'll just drop that time argument then. So this mean has to be unchanging in this case. So we sometimes just call this the mean value of x and don't put a time argument then, okay? So, and what we can, more informally, we can think about visualizing this. So let's think about what some realizations of a process would look like. So if a process is mean stationary, then we might get a realization. So let's plot x of t versus t. And it might be coming along, and the amplitudes can be varying in time. So like the variance of the process could be varying in time so that we get more range of amplitudes sometimes than others. But in this case, the mean value of the process is visually looking like it's staying near that horizontal axis. Okay. Non-mean stationary process let's draw one in a similar plot. We might have a process that's kind of increasing in time in the mean value, right? And then individual values would still be varying. But if we see this kind of trend towards an increasing value in time, that would be what a process might look like if the mean value is changing in time. Okay, so that's mean stationary. We can also talk about second moment stationary. So in this case, what does it mean for the second moment to be stationary? Well, what the mathematical condition is the expected value of the process at time t multiplied by the process at time s has to be equal to the expected value of this process where we shift both time indices by the same amount. So we'll look at time t plus r and the process at time s plus r. Okay? So if those expectations are equal to each other, then we have a mean stationary process. Right? And this has to be true for all t, s, and r. All right, so any amount of difference in time between t and s, and any amount of shifts r, if these expectations stay constant, then if the left-hand side and the right-hand side stay equal to each other, then we have a second moment stationary process. Okay, and remember we have this shorthand notation for this is an autocorrelation. So we can also write this equivalently as phi xx time t and s. That's going to be equal to phi xx at time t plus r and s plus r. Right? And so then what we can think about from this condition is that if I pick 2 times t and s, and then I shift them over to times t plus r and s plus r, and the autocorrelation stays the same, then it's not the absolute point in time that we're starting from. The t is not relevant, really. What matters is how far apart t and s are. All right? And so we can simplify this, and we can say, well, in this case, the autocorrelation, if it's second moment stationary, has to be a function of only t minus s. Right? So it's only the difference in time between t and s. Right? And for all values of t and s that are separated by t minus s, that autocorrelation is the same value. Right? So the autocorrelation is only a function of t minus s. And then it would be invariant to shifts, where if I shift t by amount r and I shift s by amount r, the difference between the two time indices is still equal. Okay, so that's the idea. And then a special case, if we think about phi xx at time t, right? So if I take the autocorrelation at time t with x at time t, if it's second moment stationary, then the t minus s is equal to 0. Right? So it's phi xx with a time lag of 0. And that's got to be constant, right? So and further, we can see that that autocorrelation, that's the expected value of x at time t squared. So it's going to be the variance of x at time t squared minus the mean value of x at time t squared. Okay. So that, so if I'm mean stationary, so that the second term is constant, and I'm second moment stationary, that means that the variance of the process has to be constant as well. Okay. So if I've got both, then we have that condition. Okay, so we can keep going. We can go to third moment and fourth moment stationarity. And in general, we'll say that this process x of t is jth moment stationary if the expected value of x at time t, and actually let's switch indices here. So I'm going to call this t1 multiplied by x at time t2 multiplied by dot, 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 up to x at time tj. So there's j terms in this expectation. If that's equal to the same expectation where we shift all those time indices by r. So it'd be x at time t1 plus r, x at time t2 plus r, up to x at time tj plus r. And this is going to have to hold for all t1, t2, up to tj, and all r. Okay, so we did this for the first moment, where it was just x at time t. We did it for the second moment on the previous slide, where we had x at time t and x at time s. You could keep adding terms in here, and if you've got j terms in that expectation, we'll call that jth moment stationary. Okay, so these are stationarity of moments. Okay, and the moments, they don't necessarily have to stack up in order. So we could have a mean stationary, or you don't have to have all moments be stationary. You could have a mean stationary process that's not second moment stationary. So the mean value is constant, but some property of the variance or the covariance is changing in time. You can have a second moment stationary process that's not mean stationary. Those are a little more contrived and a little less practically observed, but it's mathematically possible, and so on. So you can pick and choose which moments are stationary, or a given process can have some moments be stationary and not others. The case that we're going to think about a lot in this class, and it's a pretty practically useful one, is that the mean is stationary and the second moment is stationary. So the two conditions that we went through in a little bit more detail. So if we have those two, the first two moments be stationary, that's going to unlock a variety of mathematical approaches that are handy for us. Because that's a pretty common assumption or a nice case to get to, it ends up getting names. So we will talk about, I'll use kind of mean and second moment stationary, kind of spelled out. We also use this term weakly stationary. So there's some conditions that are stationary, but we haven't assumed universal stationarity. Some people call this wide sense stationary, but these names vary a little bit depending on what book you're reading or what paper you're reading. So be careful to note how exactly the authors are defining these stationarity conditions if you encounter these somewhere else. The stronger condition is if we said the process is jth moment stationary for any value of j. So no matter what moment you're looking at, that's stationary. That's called strict stationarity. Okay, so that one is a little bit more universal of a name, but oftentimes it's not necessary if we're not working with kind of higher order moments. It doesn't really matter what we assume about those. The weakly stationary is, however, quite practically useful. Okay, so that's moment stationarity. There's another type of stationarity we call order stationary. Order stationarity. So these are not stationarity of moments, it's stationarity of some other characteristics. So when we talk about jth order stationarity, what we're talking about is joint probability density functions. So a jth order stationary stochastic process is going to have the following characteristic. Its joint probability density function for x at time t1, x at time t2, up to x at time tj. And we have to evaluate the particular points. So I'll call them u1, u2, up to uj. So that joint probability density function, and this is kind of a joint density function at j points in time, that has to be equal to the same joint probability density function shifted by time. Let's do it, time r. Yeah. So it's going to be the probability density function x at time t1 plus r, x at time t2 plus r, up to x at time tj plus r. And we're going to evaluate at the same u's. Okay. And this, so it's a joint probability density function at j points in time, shifted in time by time r. If that joint probability density function stays equal, then we have a jth order stationary process. Okay? And this has to be true for all sets of the t indices. So t1, t2 to tj. So no matter what j sets of time I look at, this has to hold. Has to be true for all values of u, so all values of the process. And all time shifts. Okay, so that's in this case I just jumped all the way to the general definition. It might be useful to think back to a special case. So if we think about first order stationarity, that, now we can simplify this down. We just have a single time indices, or single time index. So that would say that f of x at time t evaluated at u is going to be equal to f of x at time t plus r evaluated at u. And that'll be true for all t, u, and r. So just as the probability density function at time t is equal to the probability density function at time t plus r for any values of t and r. So the marginal probability density function for the process is unchanging in time. Okay? So that's a first order stationarity. Second order would then go to pairwise joint distributions and so on up to jth order that we've defined here. Okay. So I think that's probably a good place to stop. We've got all our definitions of stationarity in here. So we've got moment stationarity, referring to the moments being unchanging to time shifts, and order stationarity, referring to the joint probability density functions being unchanging to time shifts. So that's a good place to pause. We'll talk a little bit more about some comparisons in the next video.